Okay, I'll tell you, it's just beautiful outside, and we wish you that are watching online have a chance to come out and visit Breckenridge. It's a beautiful place here, especially when you get so much snow. Our speaker that's going to kick off the day for our science session this morning is Dr. Jim White, who is the director of the Institute for Arctic and Alpine Research at the University of Colorado. Go Buffs, right? Go Buffs. So Jim is going to talk to us about polar change, sustainability, and why you should care. So we hope you enjoy this. And those of you online that are watching, please submit questions to your favorite meteorologist that's in the room, or just post them to the live stream, and we'll be happy to ask those questions as well. So Jim, thanks very much.
Thanks, Dave. Welcome, everybody.
Hello, Dr. White.
Hello.
Hello.
I don't normally get to speak midweek. Normally it's like, you know, the last time slot. So I don't know really how to handle the limelight here, the prime time slot you've given me, other than to dive right in. I would like to begin with a little exercise that I've been doing. I give public lectures about the topics of sustainability and resilience and climate change, et cetera, at least a couple of times a month. And I started to give a little demonstration I thought I'd share with you. So if you want to steal this and take it and do whatever you want. And it goes like this. So I do this for a while.
Thanks for the warning.
And so what I'm doing here is I'm demonstrating for you the two primary types of behavior. And there are two primary types of behavior. One of them is, we understand as physics, right? So every time I drop this pen's going to fall, right? And I can drop this pen all day, every day, for the rest of my life, and it will fall every time. It will never stop in mid-fall and just hang up. And the reason for that has to do with the fact that the universe, as we understand it, is governed by physical laws, and those physical laws are not breakable. Right? So gravity is something that happens. It happens all the time. And as scientists, we understand that. But the average person on the street, this is okay. Because the other behavior that I'm demonstrating here is free will. Right? I can stop doing this whenever I want. I can stop being annoying whenever I want. I choose. I am choosing not to do that.
Anytime, Jim.
Anytime.
All right, I'll talk.
All right. So this is something that I think that we get confused with. And I do an entire lecture on this, but we get confused about this sometimes. We get confused about those things that we can control, like free will, like stopping this pen dropping exercise, and those things that we cannot control. So we cannot, for example, control gravity. We cannot control the fact that molecules vibrate, and if molecules vibrate and you give them the right energy, they'll absorb that energy. And of course, I'm talking about, greenhouse gases absorbing energy in the atmosphere. That's going to happen regardless of what we do, regardless of what we say, regardless of what we believe, regardless of what we would like to see happen. And that's an important distinction. And I think many people who don't understand science get those things confused. They get them mixed up. What are the things that I can believe in, that I can actually have free will about, and what are those things that I really don't even get an opportunity to believe in, because they're going to happen whether I believe in them or not. Okay? So I just wanted to share that with you, in case you wanted to annoy, your viewers at any time with the pen dropping exercise, to talk about the two fundamental types of behavior. All right. Anyway, I'm going to continue on. So I've given many lectures here at this conference, and last year I think I talked quite a bit about free will, and so this year I thought I would frame my conversation around the top 5 questions I get asked at public talks. Right? And they are what you see here, and we'll go through these. Number one, are we going to make the world uninhabitable for humans and other species? I get this question a lot. Are we going to make the world uninhabitable? Because there are some people who just say, all right, we're all going to die. All right. Yeah. This is another physics issue right here. How can we insignificant humans change the entire planet's climate? Another question I get asked quite frequently. Number three, how can something like CO2 that is in such low concentration have such an impact? And by the way, isn't CO2 good for plants? Number four, we've seen about a degree of warming. Actually, we hear it in degrees Fahrenheit, but I put it in degrees C here. Why worry about such a small change? In other words, is 1 degree something that we should care about as inhabitants of the planet? And number five, and we've heard this frequently recently, I've heard that there's been no warming for several years. Does that prove that climate change is not happening? All right, I'll take you through these. And then I'm going to take you through a fair number of slides about Arctic change, which Dave wanted me to talk about. And I'm going to actually try to set up Ben a little bit here with some stuff that's going on in the Arctic and the fine work that Climate Central is doing. So hopefully I'll set a little bit of stage setting for him. Are we going to make the world uninhabitable for humans and other species? The short answer here is no. We're not pushing the climate system out of the bounds that have been observed in the past when life was present on the planet. So the simple answer to the question, are we going to make the world uninhabitable, is no, we're not. All right. Now, the better answer here is more nuanced, and it's more nuanced because climate has changed quite a bit on the planet over the years. While life has been present, but not all life. All right? So, and I'm talking now about species extinctions. So species have gone extinct frequently on the planet, and many of those extinctions we know are related to climate change, and particularly rapid climate changes. So they'll just take you through here. For the top figure here is the sort of a rough temperature record going back about 60 million years, so it's a long time into the past. But you see here that going back about 40 million years ago, the planet was about 4 degrees warmer. CO2 levels, by the way, so CO2 is a hard thing to reconstruct that far back in the past. The ice core record, which goes back about 1 million years, can give us direct parcels of the atmosphere that we can measure CO2 in. But once we get beyond that time, then we're into a variety of things here. You see how many stomata are on leaves, phytoplankton, paleosols, liverworts, believe it or not, boron isotopes, things like that. And so you see, we think that the CO2 levels, as you go back in the past, were in the neighborhood of 500 to 1,000 parts per million if you get far enough back in time. All right? So this is another important lesson. We have enough carbon locked up in coal, oil, and natural gas to raise CO2 levels to at least 1,000 ppm. But that's not a level that the planet has never seen. All right? That's a level the planet has seen before. All right? Now, this is where the nuanced answer comes in. There have been major extinctions on the planet. You can see them here on the bottom. I don't have my glasses on, so I can't read these myself. But the end of the Cretaceous, the end of the Triassic, the end of the Permian. And if you follow the line up from the bottom to the top, you see that occasionally when you get a rapid cooling, you get extinctions. And sometimes you get rapid warmings, you get extinctions. But in general, when you get changes, you get extinctions. Now, these are mass extinctions. There are as many as 30, 40, 50% of all species going extinct in a relatively short period of time. They tend to mark times on the planet when things radically changed. At least one of these we think was related to an asteroid impact. So a body from outer space coming in, smacking the planet, and changing things that way. Right. Currently, we're in an extinction. This is primarily driven today not by climate change, but by the fact that we are changing the surface of the planet. We are taking away habitat by building towns and villages and shopping malls and everything else that we build. We fragment migrational pathways. We do things to species that make it difficult for them to exist. Some species are going extinct because of climate change today, particularly those that are at the more sensitive zones. So high altitude species, Arctic species, where their habitats are changing quite a bit, are the species that we're seeing today that are being forced into extinction by a changing climate system. But most of these, what you see on here, mammals, vertebrates, birds, etc., are going extinct because of humans taking over the surface of the planet. Now this is what I think is interesting here. Every species that ever existed figured out how to survive. And that is valuable knowledge to any species that knows how to learn from it. Okay? And we are the one species on the planet that can actually digest this information and learn from it. You know, if a frog goes extinct, you might say, so what? But that frog is a species that figured out how to live and survive. All right? So it figured out how to beat the odds, how to beat the bacteria, the viruses, the predators, the changes in environment, all of those things that were going on. That species figured out how to do that. Right? And that's valuable information. If we can figure that out, what are the keys from that, we can actually learn from that. The second important point is extinctions are permanent. The definition of a species is a population that can reproduce, and once you've wiped out a species, that's it. Right? Unless it just happens to come back as a mutation that reestablishes the species. We don't think that the odds of that happening are very high at all. That means that species is gone. So we're not likely to see T-Rex wandering the planet again. Right? We're not likely to see other species wandering the planet again. So there have been some recent extinctions, and one of the things that I'm always surprised about when I talk to people about this, you know, as a planetary scientist, my view of time includes the 40 million, 60 million year time frame. I recognize that most people don't think on those time scales, but there are some things that happen even more recently. Right? So who am I? Does anybody know what this thing is on the left here? A zonkey. Does anybody know what this thing on the right is? All right, that's a rhinoceros, but that happens to be a black rhinoceros. The thing on the left is something called a quagga. Quaggas were around until the late 1880s. All right, so your grandparents probably saw a quagga in a zoo. Right? Now, the fact that none of us knows what a quagga is tells you that when species go extinct, we have a very short memory of these things. You know, they're gone. You know, we don't remember that they existed. The West African black rhino went extinct in 2011. Right? So that was just recent. And that was not big news on CNN or, you know. All right, here's a couple more. What's the one on the left? Nope. It's a great auk. What's the one on the right? Nope. It's called the Tasmanian tiger. The Tasmanian tiger went extinct in 1936, which sadly was not that long ago. And the great auk was, the last one was killed in 1844. All right. Great auk was an interesting bird. It was flightless. It used to hang around on the beaches in New Jersey. You know, you'd go to the beach for a picnic, and there's these, you know, big, large birds that would come wandering by and would, you know, steal your lunch. That's a totally different. But that's a totally different experience than what we have today, right? That's gone from our collective experience. So these are examples of recent extinctions. So, are we going to make the world uninhabitable for humans and other species? The better answer is no and yes. Climate change is a poor way to wipe out all life. And if you wanted to figure out how to wipe out all life, we can talk about that. There are ways to do it. We have the tools and the techniques. But yes, we are eliminating habitat and forcing species into extinction. And yes, climate change, especially large abrupt climate change, causes extinctions. Okay, so it's important to recognize that in changing the physics of the climate system and not changing physics, but in changing the energy in the climate system, we are indeed causing some species to go extinct, and we'll cause more and more of them to go extinct. And that is not a good way to hang into the planet. All right, question number 2. How can we insignificant humans change the planet's climate? All right, so we live on a very large planet. How can we insignificant humans change the planet? And the answer to this one is I think even more important, and that is that we are not insignificant. This is a misconception that some people have. We, as a matter of fact, in one short generation, our generation, we went from really kind of a passenger on Spaceship Earth, if you will. If you go back to the 1960s, as we used to tell us, we're passengers on Spaceship Earth. We're no longer passengers. We're in the driver's seat. we're not only in the driver's seat, but we shoved a lot of the other people off the bus, and we're tootling along. I've shown you these things before. We move 10 times more dirt than all natural erosive processes. If you add up all the dirt that flows through all the rivers and streams and blows through the atmosphere as dust every year, and you get a big number. And then you compare that to the amount of dirt we move in mining operations alone, it's 10 times more. Right? You can do this. You can go on Google Maps and you can look at coal mines in the western United States. You can find coal mines in Wyoming that you can easily see from outer space. Right? So these are very large holes in the ground that we move around. We move, and think about it, the erosive process is what's driving the entire thing behind plate tectonics. So plates mash together, mountains build up, they're eroded down. Plates mash together, mountains build up, they're eroded down. And so for us to be able to play a role in that, a very large role in that, is pretty amazing. We've talked about this before also in the past. We make more nitrogen fertilizer than all bacteria on land. This is, if you want to have life on a planet, you need to have, particularly the kind of life that we have, you need to have photosynthesis. And photosynthesis requires sunlight, it requires CO2, it requires water, and it requires nutrients. And those nutrients are generally nitrogen and phosphorus, but some smaller nutrients as well. So we really couldn't have plant life until we had nitrogen nutrients. And nitrogen nutrients are produced by bacteria. Bacteria take nitrogen out of the atmosphere, and as part of their energy strategy to survive, one of their waste products is ammonia or nitrate. And ammonia and nitrate are water-soluble forms of nitrogen, which then plants can take up and build DNA and other molecules that we have in our bodies and that plants have in their tissues, and that we need those things. So life on this planet really couldn't exist without those bacteria that are busy taking nitrogen out of the atmosphere and producing ammonia and nitrate. We figured out in the 1930s how to take nitrogen out of the atmosphere, because it's very abundant, and make it into nitrate and ammonia. And today, we make more nitrate and ammonia than all the bacteria on land, which is, if you're into biogeochemical cycles, is a pretty freaking remarkable thing to say. Because in really one short generation, we went from not being part of one of the key systems on the planet to where we dominate that key system. And we have to. I mean, we could talk more about this, but if we're going to feed 7 billion people, we've got to make nitrogen nutrients, because that's the way our agricultural systems function. We have to do that. And the scale with which we do that is the point I'm trying to make here. I'll skip sulfur here. It's a recent development. This is population going back to about 10,000 years ago to today. You can see that it really, it doesn't really show up as a large number until about 2,000 years ago. I'll blow this up more recently. We're at 7-point-something billion, 7.4 billion people today. It took about, for when we started as a species to the early 1800s to get that first billion. It took about 120 years to get the second billion, then 33 years, and then 14 years, and 13 years. And that's the exponential is a remarkable thing. And you all had to, we were talking about this at breakfast today, you all had to learn fluid dynamics, so you understand math, so you understand the exponential. But it creeps up on you, right? And as societies go, population demographers told us this was coming, but we really didn't digest this very well in terms of planning for the future. Now that has obvious consequences. You add that many people in such a short period of time, you have to add energy, you have to add water, you have to add nutrients, you have to do all the things that we need to survive. And then there's the what I call the multiplier. In order to have the kind of lifestyle that we have in the United States, in Japan, and in Western Europe, et cetera, you need a certain amount of energy, you need a certain amount of water, you need a certain amount of calories. And today, we still live on a planet in which you've got about 2 to 3 billion of that 7 billion who are living quite well, and you've got about 2 billion who are living in really poverty. They don't have food, they don't have shelter, and then you've got some group in the middle. And the group in the middle would like to live like the group at the top. And to do that, it's not a question of growing by 1 or 2%, which is what population does. It's a question of growing by 100% or 200% or 300%. So when China went from basically a third world country to almost a first world country today, the average amount of energy that the average person in China used went from, actually went up by about a factor of 300-400%. Right? And that is a huge increase. India is poised to do the same thing. Indonesia is poised to do the same thing. Brazil is doing the same thing. And so this is the big, big multiplier that drives a lot of the change that we see on the planet. So it's not just a question of having 7 billion people. It's a question of having 7 billion people who are living at a level that requires a lot of energy, requires a lot of calories, and supplying those needs for the future is a huge challenge. All right, a creature that can light up the planet like this is going to have impact on the planet. All right, that's, this has been a remarkable change in the last 20 or 30 years. We can now download pictures from outer space. Previous generations could not do that. I know that when I had this conversation with my father on a couple of occasions, the idea that human beings could take over the planet was like, wow, is that really possible? And I start to show him some of these pictures from outer space. And that was when he began to digest, yes, this is entirely possible. You see here the United States. That is Typhoon Haiyan, by the way, the picture in the Pacific there. I'm showing you that because you see on there India and China. So China is already industrializing. By the way, China is really two countries. There's about 300 or 400 million Chinese who live like we do, but there's 1 billion Chinese who want to live like we do. So there's a huge waiting thing to happen there. Also, you see on there India. So if India were to use energy like we use energy, they would need to increase by roughly a factor of 3 or 4, so 300-400% in terms of their per capita energy consumption. And you already see India pretty well lit up. So if you can imagine India becoming a first world country as well, the amount of energy that would be required for that 1 billion people to do that. And then even just recently, in 1992, you see what Europe looked like from outer space, and 2010, what Europe looks like today. So the fall of the Soviet Union, particularly Eastern Bloc countries, beginning to industrialize, then huge changes there as well. I downloaded this one. What are we looking at here? Yeah, then that big thing right in the middle is Atlanta. It's the Weather Channel. So the fact is, so the Weather Channel draws so much energy that it just lights up the sky. I mean, the fact that we can look at this and know exactly what this is pretty remarkable when you think of it. It's all because of those lights. And all of these lights, of course, are powered by fossil fuels or, to a much smaller extent, wind, solar, et cetera. Now, those things are changing, but it's still, 80-90% fossil fuels and nuclear and hydro is what's driving the show. All right. So another example of an impressive human-caused change that's already occurring and has occurred for quite some time now is something called dead zones. So I talked to you about all these nitrogen nutrients. When we fertilize our farmlands, some of these excess nutrients run down the rivers. They go into the estuaries and then out into in this case, the Gulf of Mexico, or they go in the Atlantic, et cetera. And those excess nutrients cause phytoplankton to go crazy. They love this stuff. It's like, buffet is on. It's like, all right, time to eat. They eat like crazy and then they die. Sounds like, last night to me. You eat like crazy, then they die. And when they die, their body parts have to decay. And when they decay, they suck all the oxygen out of the water. And so you end up, this red here is water that cannot support oxygen-needing life. Right? So, and this has been happening for a long time. There's huge swaths of the Gulf of Mexico, huge swaths of the Atlantic coast as well, that nothing lives in, at least for part of the year. And because it's water, as you know, it's moving around, and so that dead zone moves around and kills off a few things, and other things move in. But the fact that we can do that is another example of how human beings are really not insignificant on the planet. I'll just show you some examples here. So the map you see here are dead zones around the United States. There are dead zones around the global ocean. You can actually see the line in here sometimes if you fly out of New Orleans or out of Texas going south. You can fly over and you can actually see in the ocean a line sort of in the sand. And that's line between oxygenated water and not oxygenated water. And you can see here physically, it's a NOAA photograph. So all basic global needs, energy, food, water, shelter, et cetera, have environmental impacts. We can't live the way that we live without having an environmental impact. So in terms of food, we cultivate essentially all good farmland that's out there. We've not too much left. We grow about enough calories for 7 billion people. So feeding more people or feeding the Chinese at a higher level or the Indians at a higher will require a fundamental change. Either a fundamental change in how we grow food or a fundamental change in how we consume food. So this is sort of a heads up. This is coming, and this is coming pretty soon. That we're going to have to deal with how do we produce enough calories for all these people. Right? Water, we use pretty much all the available surface water in developed countries. So in Europe and in the United States, in many years in the United States, we use 100% of the available surface fresh water. And as you know, it gets used over and over again. If you really want to discuss to your audience, start talking about how, when we in Colorado flush our toilets, how that water goes right back in the system and goes off towards the states to the east. And they use it again, and they, flush their toilets, and it gets used again. It gets used several times as it goes along. We also pump groundwater in order to get through droughts. And we're now learning that, I won't talk about this today, but we're learning that groundwater supplies are depleting very rapidly. And so there's a day of reckoning coming there. And again, if you think about it, all right, this is a species, is this a really small, is a small species capable of pumping groundwater to the point where you're exhausting it in many parts of the world? No. I mean, this is clearly a species that has a huge impact. As far as shelter goes, about 1.5 billion people lack shelter today. And this number will grow significantly in the coming years. All right, so the bottom line is we're not insignificant with respect to the planet's capacity to support us. To think otherwise will delay action that is needed to achieve sustainable, resilient human societies. And this is this ought to be a T-shirt in much, much fewer words, but it ought to be a T-shirt. Okay, number 3. How can something like CO2 that is in such low concentration have such an impact? And by the way, isn't CO2 good for plants? Right? Shorter answer is that things that come in small sizes have big impacts. Right? We know this. Right? Try dealing with a small child, computer chips. One of my favorite artists here was only about yay tall, but he had a huge impact as well. So the Earth's temperature, so if you look at the radiative balance of the planet on the large scale, the Earth's temperature without greenhouse gases, without these small amounts of gases in the atmosphere, would be about negative 18 degrees C. We know this. We have satellites at the top of the atmosphere that tells us this is how much solar energy we're getting. And if we were just a rock in outer space with no atmosphere, we would be about negative 18 degrees C on average. And most people would argue that's too cold for advanced life. We couldn't exist as we are on the planet. Now, the Earth's temperature with thermometers taken out there is about 15 degrees. And the difference between negative 18 and plus 15, about 33 degrees C, is the impact of these very small amounts of gases that are in the atmosphere, these greenhouse gases. They raise the temperature of the planet by a large amount. Okay? And that's a good thing. Right? So if we didn't have greenhouse, we need to recognize that. If we didn't have greenhouse gases, we would not be a liquid planet. We would be a frozen planet. And that would obviously be a very, very different situation for us on the planet. So when I get this question about how can something that's 400 parts per million make a difference, we'll talk about water. All right? So water, the average percentage of water vapor in the atmosphere over the U.S. is about 1%. Now that all those pictures that you see there exist because of that 1%. All right, so you've got crops, you've got plants, you've got precipitation, you've got wonderful, lovely green things that exist because of 1%. All right? So this is an important, again, when I get that question, how can something at 400 parts per million make a big difference? Well, how can something at 1% totally change the surface of North America? And the answer is small things have big impacts. Right? Isn't CO2 good for plants? And the answer is yes. As I pointed out before, plants need CO2, they need sunlight, they need water, and they need nutrients to grow. All right? So, if you give plants more of any of those things, will they do better? And the answer is generally yes. Biology tells there are limiting factors. So, for example, if there's no nitrogen available, it doesn't matter how much water you give a plant, it's going to die. Right? So, but if there's enough of these things around and you add more, then you're going to get a boost in plant growth. So imagine the sun was heating up, for example. We had a much hotter sun, giving the plants many, many more photons to do photosynthesis. Would they grow more? The answer is likely yes. Right? You can do that. You can take plants into a greenhouse and give them artificial sunlight, and they'll do better. They will grow more. Now, would it become unbearably hot? And the answer is yes, it would become unbearably hot. Right? And the important thing to recognize here is that, you know, good things always in moderation. All right? So down here on the right is my little bourbon, homage to bourbon. I won't drink much, drank way too much, hangover, I'm never drinking again, repeat. All right? That's how we work. All right? And we hear this quite a bit. This is Jeff Sessions here. Carbon pollution is CO2, and that's not really a pollutant. That's plant food, yes. And it doesn't harm anybody except it might include a little temperature increase, yes. All right. Does it really harm anybody? Yeah, as a matter of fact, yeah. So again, good things in moderation. Now, plants are growing more. All right? This is one of the more remarkable observations that we have today. This is, on the left here, you see the sources of carbon from 2006 to 2015. It's 91% from fossil fuels, 9% from deforestation. And on the right is a partitioning of where that stuff is gone. And this is one of the things that I do in my research. I use carbon isotopes and other things to try to figure out how much of that CO2 stayed in. We know how much stayed in the atmosphere. We can measure that. How much of that went into land plants versus how much goes into the ocean. We can actually figure that partitioning out using something called carbon-13. But from 2006 to 2015, about 31% of the carbon that we put in the atmosphere is now in land plants. It has increased the amount of land biomass that's out there. About 26% of it dissolved in the ocean. And the ocean would like to run the show, and so the ocean is going to take in some of that. And about 44% of it's still in the atmosphere. All right, so is CO2 plant food? Yes. Have plants been growing more? Yes. All right. Despite deforestation, there is more biomass on the planet today than there was in the 1800s, which is pretty remarkable. Because if you've followed deforestation, we are deforesting today, and we have deforested since we started out as a species. And there's definitely less large forests, particularly in tropical areas today, than there has been at any time because of us. This is a little graph that shows that. On the left-hand side here, you see the atmosphere starts out about 280 parts per million. You add some carbon from coal, some carbon from oil, some carbon from natural gas, some carbon from concrete, and then some carbon from deforestation. And then at that point, you see the sinks, how this stuff is removed. So the land removal there is larger than the deforestation. Not by a whole lot, but it's larger. And then you see the ocean uptake, and you see the atmosphere today at 400 parts per million. So this is the best accounting that we can do and this is from 1870 to today. So the fact is, yes, plants are doing better. Now, it's important to recognize that we can't grow our way out of the increase of CO2 in the atmosphere. And the reason I can say that with confidence is that there is way more carbon in coal, oil, and natural gas than there is in all living biomass on the planet. All right, so if we wanted to grow plants to remove all carbon dioxide, we would have to have not only this planet, but we're going to have to rent 2 or 3 other planets in order to make that happen. We don't simply don't have enough biomass. We don't have enough land surface. And at the same time, we also compete with land plants for the land surface. We need land surface to grow crops. And that means you don't have space for trees to grow that you would have otherwise. And so, no, you can't grow your way out of this. You can also look at this. This is now over time from the 1880s. You see on the top here are the sources, land use, deforestation in the brown there, fossil fuels. And then you see the sink, so the land sink, the atmosphere is where it ends up, and the ocean sink. The land sink changes quite a bit. This is climate. This is weather. This is, some years are good for growing. For example, this is going to translate into quite a bit of biomass in California and in Arizona when it melts. All this stuff outside here. Okay, so when you got a good snow year, we grow a lot here in the West. When you have a good snow year, some of that water goes east, and Kansas and Nebraska also do well. Okay, number 4. We've seen about 1 degree C of warming. Why worry about such a small change? And this is one of the more important questions, I think, and I really like it when I get this question because I think it shows that people are thinking about this. 1 degree, is that really significant? Is that really important? All right, so let's take a look at what 1 degree means. So this is the last 2,000 years or so. You see the various temperature records we have here. The increase in temperature that we're talking about is here on the right. It's about 1 degree C. You see that there's quite a bit of variability over time. So over the last 2,000 years, 1 degree is really not altogether that significant in terms of the various changes that have occurred. It is significant, but it's not hugely significant. If you take this back farther in time, this is 400,000 years. This is now the Vostok Ice Core going from today back 400,000 years, and you see a temperature record there on the right. So 0 would be today's average temperature. So we think that during the various interglacial periods that existed, about 120,000, 140,000, 240,000, et cetera, roughly every 100,000 years in the past, we think it was warmer during many of those, including the last one. And we have fairly good records accessing the last interglacial period. We think it was about 2 degrees C warmer at that time. Okay? Now that's helpful because I will loop back and I'll show you what are some of the key metrics in terms of how the planet looked with 2 degrees of warming. I would point out, by the way, so 2 degrees is not a number that I'm just pulling out of my head. 2 degrees is what, right now the global leaders are arguing over whether or not we can achieve a plateau at 2 degrees. And some people are saying, no, it's got to be 1.5. So 2 is an important number here. Right? 2 is a number that we should pay attention to because it's a number that we've been told is got some safety to it. If you go above 2, bad things happen. If you stay below 2, good things remain. I don't believe that is particularly the case, but that's the number that's being thrown about today. If you go back about 3 to 5 million years ago, you'll find the planet was warmer at that time by about 2 degrees. So again, you see the scale here on the right. This is fairly well documented. This is ocean bugs that live out there that record temperature. And 5 million years is quite accessible in the ocean sediment record. So we're pretty confident that if you go back 4 or 5 million years ago, you get temperatures about 2 degrees warmer. By the way, 3 to 5 million years ago, CO2 levels were about 400 parts per million. And so that's one of the reason why we think that the temperature was warmer at that time was the CO2 levels were higher by about 400 parts per million, or up to around 400 parts per million. If you go back farther in time, you'll find that if you go back about 40 million years, the planet was about 4 degrees warmer than today. That's a significant point in Earth's history because Antarctica started roughly at that point in time. So if you go back about 40 million years, and that's when the planet cooled off enough that Antarctica started. And you see the planet was as much as we think about 12 degrees warmer if you go back about 60, 70, 50 million years ago. Now the cool off there we think is CO2 related because that's where you have records of CO2 at about 1,000 parts per million 50, 60 million years ago, and then it's beginning to cool off. By the way, it's dinosaur time. That's coal formation time. That's oil formation time. That's the planet was doing really well in terms of photosynthesizing a lot at that time. And I'll come back to that 4 degree mark too, because that's an important mark in Earth's history. So is 2 degrees significant? And the short answer is yes. All right? It was about 2 degrees warmer in the last interglacial period. sea level was about 5 meters higher at that point. Right? 5 meters higher at 2 degrees. And that was about 1,000 years of warmer time. Right? So keep in mind that it takes a while to melt ice, and we'll talk about that in a minute. It was about 4 degrees warmer when the Antarctic ice sheet did not exist, and sea level was about 80 meters higher at that point. So there's about, between Antarctica and Greenland, there's about 80 meters of sea level that's been taken out of the ocean and put down as land ice in Antarctica and Greenland. And that's an important lesson for, again, those of us who look at deep Earth's history. This is like no big deal. Yeah, constantly we have sea level rising or falling and land ice doing the opposite. That's just the way the planet functions. But for many people, the idea that sea level could be 80 meters higher, when you actually look at the maps, is like, this is one of those holy shit moments. In the last 40 million years, the full range of temperature change has been about 10 degrees C. That includes no ice sheets, and that includes large glaciations. Right? So no, 2 is not insignificant. 2 is a decent part of 10. Right? If you take away the glacial side of that, which is about 6 degrees, it got 6 degrees colder during the last glacial period. The warming that we've seen over the last 40 million years was about 4 degrees. Right? And we saw huge changes on the surface of the planet that accompanied that 4 degrees. So no, 2 degrees is not insignificant, and 1 degree is not insignificant. I've heard there's been no warming for several years. Does that prove climate change is not happening? No. Physics still applies, all right? Global climate depends on 3 factors. We know this. How much energy we get from the sun, that's physics. How much of that energy is reflected back to outer space by the white bits, physics. And the amount of greenhouse gas, which is controlled by molecular vibrations, again, physics. All right. So if you increase the amount of greenhouse gases in the atmosphere, you will change the amount of energy in the atmosphere, and you will change, therefore, the climate on the planet, because the climate on the planet is indeed the energy in the atmosphere. So also keep in mind, and we saw this, I think it was yesterday or 2 days ago, our focus tends to be on air temperatures because we live in the atmosphere. The ocean community thinks we're pretty, selfish, and the fish out there, they get together occasionally and say bad things about us. But the fact is, 90-something% of the heat capacity at the surface of the Earth is in the oceans. You saw, I believe, the figures 0 to 700 meter heat content in the ocean over time. This is the 0 to 2,000. It's known with less precision because you go but it includes most of the ocean. Right? So ocean heat content has been increasing over time. It has not gone through any major, dips and wiggles. And the reason for that is that, this is as you accumulate greenhouse gases in the atmosphere, you accumulate energy in the atmosphere. As you accumulate energy in the atmosphere, it has to go someplace. And it can go to evaporation. It can go to temperature. If it's going to go to temperature, it's going to warm the ocean up. And if we got a good accounting of how the ocean is behaving, you'll see that this keeps going up over time. Yes?
Lika Guha Thakurta, I'm at NASA headquarters, heliophysicist.
Yeah.
I've been very interested in the energy input from the sun, and typically that is in the form of the total energy input that is often used by climatologists, the total solar irradiance. So some of these models that you're showing, are you also considering sort of variation at the spectral irradiance, which, CU does a lot, and that actually has a different path of propagation through chemistry, transport, all of that, and gives sort of a regional variability also. Do you have any thoughts or comments on that?
Yeah, no, you can, the topic of the energy balance of the planet is complex. And you can get into some differences there. You can get into some, I would say, nuances. Not to belittle what you're asking is a very important question. What I'm doing here is giving you the 30,000-foot view, as I would give to the general public, right? And so, yes, I appreciate what you're saying, but if I went there, I'd be in the weeds very quickly, and I would lose people very quickly. So the atmospheric temperature is really the tail. It's the ocean that's the dog, and we need to pay attention to the ocean. Right? And you can see on there, yes, indeed, the atmospheric temperatures plateaued for a while or slowed down their growth, however you want to say it. And that's what you expect. You expect that on a planet that is 70% ocean. When you have times in which cold water is circulating up to the surface, it air conditions the atmosphere. When you have times when deep ocean is not being allowed up to the surface, the surface ocean warms up very quickly, and you end up with a much warmer planet. This is what a phenomenon of El Nino and La Nina. All right? So we know this. There will be times when atmospheric temperatures bounce around a little bit, but they are the 7-8% of the heat capacity. If you really want to understand what the planet is doing, you need to understand the ocean. Yeah, I can see your hands on the microphone.
Greg Fischel, WRAL in Raleigh. I just wanted to make sure that when I go out and give talks that I'm saying the right thing.
Yeah.
That I tell people that natural variability did not go away when we started burning coal.
No, natural variability is still here.
So there still are cycles that go up
Yes.
and down. And so the one thing I've done, it's oversimplistic, but I'll plot a graph y equals x equaling the steady increase in CO2, and then the sine of x being the natural cycles. And when you add the two functions and they're in phase, it goes up,
Right.
but there are times when they're out of phase and it flatlines.
Right.
So is that a fair way to
Sure.
Okay.
Yeah, no, without getting too complicated, it's really a question of heat storage in the ocean. So the ocean has by far most of the heat storage at the surface of the Earth. And when you have a time in which cold water is allowed up to the surface, which you have when you have strong winds blowing the ocean away from the eastern coast, or the eastern side of the Pacific Ocean, eastern side of the Atlantic Ocean, warm water or cold water comes up, and it cools the atmosphere off. So you see that. We can see that in El Nino and La Nina. We see that in Pacific Decadal Oscillation. We see a lot of the variability on the planet in terms of these kind of yearly to decadal kind of changes are driven by whether or not you've got cold water accessing the surface or whether you don't have cold water accessing the surface. And when you don't have cold water accessing the surface, we can warm up quite a bit. But keep in mind that there's still a huge amount of cold water lurking below the thermocline, lurking below down in the ocean. Right? And so this is part of the message of change is that it takes a generation or two for what we put in the atmosphere to have its full impact on the planet, because it takes a while to warm up the ocean. In public talks, I tell people, imagine you put two pots on the stove. Right? One of them you put a quart of water in, and the other identical pot you don't put any water in. And you turn the heat on identically, so you put exactly the same amount of BTUs or calories into both systems, and go away for 2 or 3 minutes. Come back, you can put your finger into the water, and it may be a little bit warmer, but not much, right? And this is a thought experiment, because you'll see why. Put your finger in the other pot, and the sizzling sound you hear is the end of your finger burning. Energy cannot be created or destroyed. The same amount of energy is going into both of those systems. So why is it the water pot is barely warm, and this pot over here is screaming hot? And the answer is heat capacity of water. It just takes a long time for that water to warm up. Okay?
Better plug in, baby.
Your battery's running low, man.
Could not be destroyed. Make up your mind.
I'm feeling really. We need some electrons. So that, and then how the ocean behaves in terms of particularly the deep to surface circulation is extremely important for these, for the kind of variability that we see on 10, 20, 30, 40, 50 year kind of time scales. It's not going to go away unless the ocean fundamentally changes and quits circulating, which would be a very bad thing. Oh, now that would be an enormously bad thing, an enormously bad thing. Life on this planet depends on nutrients from the ocean depths coming up to the surface, and so all of that really is the whole system depends on having a liquid ocean that circulates around. Okay. Thank you. My technician here is. Can you work on my legs when you're down there? So this gets, somewhat to your point, attribution of change over the last 100 years. So what you see here is, if I can read this correctly, at the top here you see the global surface temperature observations. There's a volcanic component, so this is the reflectivity part for the most part. So on this kind of time scale, the big reflectivity change is in whether or not a volcano went off and put sulfate up in the stratosphere. There's internal variability, and you see the internal variability percolating along quite in a healthy fashion. And then the anthropogenic component, of course, follows our trajectory over time. Right? And one of the reasons why we think that we argue about when did the Anthropocene start? When did human beings really reach a point where we're the number one thing on the planet? And if you look on there, it's really in the 1980s where the amount of greenhouse gas in the atmosphere really begins to shoot up. And the warming, particularly that followed that time, we can't attribute to anything but the increase in greenhouse gases, which is a human-caused thing. All right. Now I'm going to spend the rest of my time here focusing on ice, and then we can have Q&A. I blasted through that, which is fine. Yeah. All right. So I want to focus on ice. So why? So there's two simple answers here. One is sea levels rising, and Ben's going to talk a lot more about that. And will continue to rise to levels that are frankly shocking. Right? And this is, when I talk in public, people will say, can you give me some idea of what it means for sea level rise? And I say, yeah, there's no more Miami Beach. And there's no more Miami. And there's no more Norfolk. And, they look at me like I'm a little weird. No, they look at me like I'm a lot of weird. Because that's very difficult for people to digest, very difficult for them to comprehend. And I think one of the educational components that we need to do much better at is really educating people about this is how your planet functions. Your planet trades land ice and ocean all the time, and not in small amounts. Okay? And I'll try to quantify that for you. We do, however, need far better information on how fast it will occur and ultimately how far sea level will rise. But in red here is important. We know that it will rise and to levels that will cause unprecedented damage and costs in the future. The second is sea ice is rapidly shrinking, and that is a potential weather trigger. I think it was 2 or 3 years ago, Jennifer Francis spoke here. We've had her out a couple of times. There's a whole community now of scientists who look at polar change and try to map polar change into change that we see down here in the continental United States and at 30, 40 degrees north. And the evidence is getting stronger and stronger that as the energy balance of the Arctic changes, that impacts the weather that we have down here. It impacts how the jet stream functions. It impacts how rapidly storms move or how slowly storms move. It impacts how far cold air can exit out of the Arctic region. So there's a lot of things that are happening, and you all know this. The last 5 to 10 years have seen some rather unusual weather events. And I think that's just, we got to sort of buckle our seatbelts, put our tray tables up and go, okay, this is what's going to happen. We sort of figure out why and what's going to happen in the future, but I don't think there's any reason to expect that to change because the energy balance of the Arctic is changing quite a bit. Why am I so confident in all that? One is that water has a tipping point, or ice has a tipping point. It's either ice at 32 or it's water at 0. And tipping points within the climate system are really important. So when you hit a tipping point, you can have very rapid change. And snow, whether you have snow on the ground, you know this, whether you have snow on the ground and therefore you have more reflectivity, or whether it rained and you have water that goes into the soil, is very different. It's going to make a big difference to the weather for the next several days. And And indeed, it's going to make a big difference to the weather for the next several months in terms of the climate. Second, warm water and warmer air melt ice. All right, this is how it functions. Third, warm water does expand, so there is a thermal expansion component of sea level rise. And fourth, it's physics. All right? This is not something you get to believe in. This is one of these things. Right? All of these things are going to happen. It's not stopped yet. Right? Maybe one of these days. Right? Polar changes are important to watch. This was discussed the other day. Why? Because polar amplification makes changes larger, easier to see, and the poles are where we expect to see changes first. All right, so in 2016, I pulled this off of NOAA. The Arctic had its warmest year on record, and that's driven by several factors. One is a decreasing sea ice. Trading white ice for blue ocean is a very, very big albedo effect, a very, very big heat storage effect. And second, snowfall, as particularly in the shoulder months of the spring and the fall, when you have less snow in October and November, you have more heating, and you have less snow in April, you have more heating. And so those shoulder months are really important. As a paleoclimatologist, as a paleoscientist, we can track this over time. This is the way the planet has behaved for as far back as we can actually see. That if you look at, for example, that 2-degree change I told you 3 to 5 million years ago was a 6-degree change in the Arctic. That 4-degree change that you saw with no Antarctica was about a 12, 15, 16-degree C temperature change in the poles 40 million years ago. Right? So these are very big changes in the Arctic. And that factor of 3 or so, we call the polar amplification factor, has been active for a long time. And the reason why it's active is because it's basically physics. This is snow cover, looking at historical and then predictions. I don't have the definitions of all of these. These are all, the RCP 8.5 is the business as usual scenario where CO2 goes. I took a lot of the slides out that had all that stuff in there. All those others on there, the gold and the blue, are very rosy predictions for what would happen if we got off of fossil fuels or if we reduced CO2 in the atmosphere by geoengineering or whatever we did it in a big fat hurry. So if you look at RCP, for example, 2.5, that's pretty much today stopping CO2 and slowing down, as a matter of fact, removing it from the atmosphere. So this is one of the important things to recognize. If you look at any of these predictions for the future, the Intergovernmental Panel on Climate Change in particular, most of those scenarios are we know, very, very rosy, and they're not happening. And the one that is happening, the RCP 8.5, is the one that looks the scary side of things. Right? So it's important to recognize that certainly one of the more conservative groups out there in terms of looking at future climate is the IPCC. So you see snow cover changing over time. You guys know what that does. I won't talk much more about this, but permafrost is also decreasing. So permafrost is frozen land. We've had, for the last 10,000 years, some pretty stable temperatures on the planet, and they included a large chunk of Canada and a large chunk of Russia that were frozen. In those systems, in those really cold systems, it thaws out enough in the summertime that you get some photosynthesis. So there's land plants that they grow up there. But then during the wintertime, when normally you would have respiration and that carbon going back up into the atmosphere, which happens here at 40 degrees north, it doesn't happen. That's not the way it works when you get that far north. It freezes up, and that carbon gets stored for the most part. And so really cold regions of the planet tend to store carbon over time. And indeed, permafrost has stored carbon at a rather large amount. There's about as much carbon stored in permafrost as there is in all coal, oil, and natural gas put together. And that's frozen. And that has that 32-degree mark set into it. It doesn't all freeze at once. The good news is the physics still applies. It takes a long time to melt this stuff. You start melting it at the surface, and you melt it down, and you melt it down, and you melt it down. It takes probably 100 years or more to melt permafrost. But once it's melted and accessible to bacteria who love to munch on this carbon, then this carbon starts to come out. It comes out as CO2, comes out as methane. We can talk about that more. But this is one of those feedbacks that as a carbon cycle scientist, we worry about quite a bit. It may be that what we do as human beings starts to get overshadowed by what the natural carbon cycle does as the permafrost systems begin to warm up. So trading seawater for land ice, this is how your planet works. What I've plotted here now, I stole this from Foster and Rowling in a proceedings of the National Academy of Sciences, is CO2 and sea level. And you see CO2 varying from about 280 parts per million to about 180 parts per million. And that was that's the glacial, interglacial kind of change. You go from about 280 parts per million down to about 180 parts per million. It's about 100 ppm change. By the way, you can do the math really quickly. So 280 to 400 is bigger than 100. And so we've actually increased CO2 in the atmosphere more than the CO2 decrease that accompanied the large glaciations on the planet. Now, those large glaciations weren't driven entirely by CO2. As a matter of fact, they were driven predominantly by changes in the Earth's orbit around the sun, which gave us less sun. But CO2 was a contributing factor. You see the very good relationship here between CO2 and sea level. Now, the scale here on the right is the one I want to focus your attention on. 0 is today's sea level. So when it got colder, that 6 degrees cooling on the planet that I talked about was about 120 meters of sea level drop on the planet. So you took about 120 meters out of the ocean of water, and you made it into Antarctica, and you made it into Greenland, and you made it into the Laurentide ice sheet, and you made it into the Fenno-Scandinavian ice sheet, large chunks of ice on land. So that was a very large change there. You'll also notice on there that sea level was, you see 120,000 years there. By the way, I apologize. Sometimes time goes from left to right. Sometimes time goes from right to left. But you see 120,000 years on there. Sea level is about 2 meters higher at that time. It doesn't look like a big change there because the big change that you see on this particular graph is the glacial change. You also see that at various times in the past, sea level has been about the same as it is today. It's been maybe a couple meters lower, maybe a couple meters higher. This translates that into a graph. I think I've showed this in the past. This is a simplistic look at it from a friend of mine, Dave Archer. You see sea level scale there going from 100 meters higher to 150 meters lower. You see global temperatures there going from the lowest point there on the left 20,000 years ago is about 6 degrees colder than today. Average temperature on the day was about 15, if you remember. I talked about that earlier. So it's about 9 degrees at that time. The Eocene, about 40 million years ago, you've got about 80 meters higher sea level and about 4 degrees warmer. Right? And so this is I've talked about this in the past, and this is one of my most, I want to get out to the public messages that that 10 degree sea temperature change that we had on the planet was accompanied by a 200-meter sea level change. All right? So you go from today into the past, 6 degrees colder, 120 meters. You go from today into the future, 80 meters, 4 degrees. So the scaling is not linear, and I'll show you another graph in a second that really illustrates that. But it's important to recognize that on average, every degree of temperature change is about 20 meters of sea level. That is a huge number. But that's what the planet does. All right? To the planet, this is no big deal. This is what we do on a regular basis, folks. This is how we handle things. Right? I think it's us as human beings who have built large cities. We've built huge amounts of infrastructure right on the coast, thinking that sea level was going to stay where it was. No, it doesn't. All right? Whether we make the changes or whether the planet makes the changes, it doesn't really matter. The fact is that sea level is a very dynamic thing on this planet. Jim.
Jim Gandy, WLTX in Columbia, South Carolina. The sea level, over that rise, that change, over what time period did that change take place?
I'll talk about that in a second. Thank you. That presages one of the slides coming up. This is a more nuanced look at the graph I just showed you. This is now atmospheric CO2 plotted as a log function, and that is the forcing function. So As CO2 increases and increases in the atmosphere, you get less and less of a bang for your buck because CO2 begins to compete with itself. Okay? So you really ought to plot it not as a linear function, but as a log function. And then against sea level, and the sea level scale is, again, about 200 meters or so on here. What's important to note on here is that if you go into those green points, so from today into the past, you see a very large tailing off. So we know that as you take CO2 out of the atmosphere down to around the 180, 200 parts per million level, planet cools off quite a bit, ice sheets can grow. All right. You also see on here probably one of the more disturbing messages in here, and that is that somewhere around 600 to 800 parts per million in the atmosphere of CO2 is when you have Antarctica as an ice mass or you don't. Or you have 80 more meters of sea in the ocean. Right? So now, we can talk more about this because one of the more interesting questions is that we've watched Antarctica form, but we've not watched Antarctica go away. So Antarctica forming, all right, when you reach that 800, 700 ppm threshold, that got cold enough that you started to develop Antarctica. Right? Now, does that mean that when you reach 700, 800 ppm in the atmosphere, you start to melt Antarctica? And that's a fundamental question, and one that I don't think we know the full answer to. Although, if it went one way, I think, precautionary principle would say, all right, it's probably going to at least be in the ballpark going in the other direction. We're at 400 today. Will we make 600? Will we make 700? Easily. I mean, if we don't change the way that we're doing things, we'll easily get to 600, 700, 800 parts per million. Right? We can make 1,000 parts per million. And we can do that in a far shorter period of time than we give ourselves credit for. We can my kids, if they use energy the way that my generation used energy, they will need all of the coal, oil, and natural gas that we have in order to do that. And so you could very easily change the amount of CO2 in the atmosphere by large amounts. And so this is an important. So the other important thing to look on there is that orange bar. That orange bar is important because it's about 14 meters, 15 meters higher sea level today than today. And that 14, 15 meters, so there's a lot of scatter in there, but there's an amount of sea ice amount of land ice on the planet that is dynamic, that can change quite a bit. And that's that 14 meters. Once you go to, this is what's called the marine-based ice, and I'll talk more about in the next few slides. But the marine-based ice is very dynamic, and it can waste fairly rapidly. And as a matter of fact, the planet would, from a simple physics point of view, would love to shed about 14 meters of land ice into the ocean. That's where we would like to be today. Right? 14 meters is, again, something that's a problem. Right? So a little bit more about marine-based ice. So there are parts of both Greenland and Antarctica that the base of the ice sheet is below sea level. And that is fundamentally, and that's unstable, what we call metastable. So this is particularly true in West Antarctica. You look on the right-hand side there. Most of West Antarctica would be an ocean if the ice went away. You see the plots there at the bottom where the ocean level is and where the ice is. Now you might ask, well, how do you even get ice there in the first place, right? So, and the answer to that is twofold. One is that, remember, 20,000 years ago, sea level was 120 meters lower. So a lot of these large land ice masses grew at that time, and there was no sea level to bother them at that time. And then as the deglaciation occurred, as the Laurentide melted and all these other ice sheets melted, sea level rises, and you create what we call a metastable situation, where now you've got land ice that has its base below sea level. And it would, at some point, like to just dump that ice into the ocean and get back to what we would think of as a normal situation where the ice is floating in the ocean, or the ice is melted into the ocean. And there's about 14 meters of that. This is another way of looking at that. The land ice comes out, tends to hit something called an ice rise you see on there, where it doinks and can hold itself. This allows the ice sheet to build more and more land ice up, but it also keeps warm water from penetrating in there and melting the base of that ice sheet. The key here is you've got to have cold water cold ocean water that doesn't have a lot of calories in it to melt land ice. And it's really ocean melting that is the thing that we think about more in terms of melting these ice sheets than the atmospheric temperature, because that's, again, the heat capacities in the ocean. So, thank you. Another important, so by the way, once that ice rise is breached, once warm water is able to melt that contact point, then it can basically melt back. And we don't think that there's anything that stops that ocean water from melting that land ice until you reach the point where you're back above sea level. Right? So basically, West Antarctica, we think, is a situation in which once that protective ice rise is breached, that ice is going to come out, and it's going to come out. The good news is it doesn't come out very fast. Ice flows relatively slowly. But the bad news is we don't think it's going to stop. The bad news is that there's 14 meters of marine-based ice in Greenland and Antarctica, and it's being, what's the word? It's being melted, the contact's being melted. It's being put into a situation where it can start to flow into the ocean. And once it starts to go, we don't know that there's any way that stops. So that's an important lesson for us.
Is that what's going on with Larsen C right now?
Larsen C is a large floating chunk of ice.
But if that was to move off, then
Yes.
what behind it would be able to,
Yeah.
to move it.
No, it's a very good point that once, so these, as a matter of fact, what I'm showing you here is that buttressing that you see there with the ice shelf. The ice shelf helps, even though it's floating, it helps to buttress the ice. And so in Larsen C, when these big ice sheets, these big ice shelves melt and go away, we've seen this before with Larsen B and with other pieces. The land ice flows out much, much faster as time goes by. What's new here is something interesting, is the importance of ice cliffs. So what we found is that as these ice shelves are peeling off and going out into the ocean, you end up with larger and larger ice cliffs. And rock can have very, very high cliffs because it's structurally sound. Ice is not so structurally sound. So once ice gets to a couple of 100 meters, it just falls apart naturally. It can't, gravity is a strong enough force and ice is weak enough that it begins to collapse under that. So this was something that's just been added to our ice sheet models, and this affects the pace with which ice sheets erode. That once you start to break these things down and you form these large cliffs at the edge of the ice sheet, those cliffs fall down much, much faster than we thought that they did in the past. That increases the rate of sea level rise, obviously, because it's not just a question of how rapidly can ice flow, it's a question of, how, once it starts to peel off, that helps to, then the buttressing goes away even more, and you start to move ice into the ocean, and hopefully that all makes sense to you. It's all about keeping that buttressing in place, and if the buttressing is not there, then the ice can flow.
Jim,
Yeah.
Joe Murga from WTAJ.
Joe.
Do you get seismic activity from it? I mean, are we seeing that?
Yeah, no, you can actually see, the geophysicists put the little seismic gizmos out there and actually watch this stuff. And you can watch that it, it has precursors and then it begins to go and you see large chunks of ice fall off and you see the seismic signatures of that. Okay, so this I think gets more towards what we're going to see in the second talk of the day, the declining ice mass in Greenland now. This is showing from the GRACE satellite. GRACE is a gravity measuring satellite. And the gravity measuring satellites, I think, is some of the best stuff that we have. It measures mass. And a lot of other satellites, if you measure the surface of an ice sheet, that surface of the ice sheet can vary depending on the density of the snow. So if you can make that surface go way up, but if you make it go way up with very light snow, there's not a whole lot of mass there. So I think mass is the thing to measure, and GRACE has, I think, helped us out quite a bit. So I want to show you a couple of movies here. So this is the Greenland mass loss from 2003 to 2013, showing where it's occurred. The darker colors are where the ice has gone away. And you see that it's not all uniform, and this is what we expect. So Greenland is a chunk of land here, but it's got, just like North America, there are river systems underneath the ice that go into the ocean. There are places where ice can more easily flow into the ocean, places where it's harder for it to flow into the ocean. And you see here the places where it's easier to flow into the ocean are the places where you're seeing more and more mass loss. And that's pretty much exactly what you'd expect. This is now put into a set of pictures here showing where the mass loss has been for Greenland. This is what we expect to see. So this is looping back to that we were talking about earlier about the interglacial and the 40 million years ago. Modeling the Greenland ice sheet is something that we're trying, but I don't know that we're all that good at it. This is looking at various models that are out there. We know that sea level was about 5 meters higher 120,000 years ago. We know it was about 2 degrees warmer. Some of that came from Antarctica, some of that came from Greenland. The amount from Greenland, the amount from Antarctica is something we argue about as polar scientists a lot. It does make a big difference to us. It doesn't make a big difference to us because once that stuff goes into the ocean rises. And so in the end, it's not a huge deal. But it is important for us in terms of where do you watch? How much do you monitor Greenland? How much do you monitor West Antarctica? How much do you monitor East Antarctica? The same lesson we learn in the southern hemisphere. This is now on the right here. You see it 128,000 years ago with a bunch of feedbacks put in there. You see that the West Antarctic ice sheet was pretty much gone. And I'm an ice core scientist. I've spent a long time trying to figure out whether or not the West Antarctic ice sheet was there during the last interglacial period. And the best answer we can give you is no, it wasn't there. And as a matter of fact, in order to get 5 meters of sea level, you've pretty much got to make West Antarctica go away. And so that all makes some sense. If you go back 3 to 5 million years ago, you see a picture here of the what's called the Pliocene. We think something in the neighborhood of 11.5 meters of sea level coming off of Antarctica at that time. Again, that's 2 degrees. But that's 2 degrees sitting for quite a while, for thousands of years. Right? So, we're in the midst of a climate change, but how climate changes will be critical to adaptation. And in adapting to climate change, the old adage, speed kills, is important to recognize here. The faster things occur, the more of those species extinctions you have. The faster things occur, the more, what Ben is going to tell you about the coast is going to occur. So all the things that we worry about, the faster they occur, the less time you have to adapt, the less time you have to deal with these things economically, deal with them socially, et cetera. So understanding and preparing for abrupt change is, I think, critical. Now, back to your question, Jim, about sea level rise in the past. On the right here, you see sea level rise that's been measured over the last 2,000 years, over the 20th century, and over the what's called the satellite altimetry era, which is less than the 20th century. Basically, as our planet has warmed up, the rate with which sea level is rising has increased, and that's perfectly sensible. That's physics. That's the way it ought to work. But we're seeing rise rates here of about 3 millimeters per year over the last 10 years, 15 years or so. That's actually relatively small compared to what the planet has been capable of doing in the past. So if you look at the deglaciation, you look at how rapidly was sea level rising throughout that time period, rates that are in the neighborhood of 3 times faster than that, 10 millimeters per year, are typical. So that's what you see there on the left bar. And there are periods when you've got large chunks of ice that destabilize. We don't know exactly where these things are, but large chunks of ice that destabilize and go into the ocean rapidly. Meltwater pulses, they're called. And they happen 2 or 3 times during the deglacial. So sea level crawls along at this 10 rate, and then we'll go up to 40, 50. So 10 times faster than today. Yeah?
What's the rate of change in that 40 to 50?
Excuse me?
How long does it take for that pulse?
Oh, those pulses are typically no more than a few centuries. So, and this is something we've talked about in the past. We're looking at something like a meter sea level rise over the next 100 years or so. That's sort of conservative. This is what's going to happen. A meter in 100 years is something that, yes, we ought to really care about because it is really significant for coastal communities. But it's hard to get people really excited about that, even at that level. A meter in 30 years, that's a mortgage. A meter in 30 years is much more significant. And we think that that's pretty much the sort of the typical rate that the planet does when it starts to shed ice. And so this 14 meters, we think, rates of roughly a meter in 30 years, let's say 3 meters in 100 years, is probably what we ought to think of as sort of an average rate coming in the next few centuries. There are, of course, tipping points along the way there. The Federal Flood Insurance Program we could talk about. Either that's going to be the largest entitlement program on the history of the United States, or it's going to have to go away. Property values, this is a really significant issue. When you can no longer get insurance, what happens to the value of homes near the coast? Is that going to, and we know this, it's humans, we don't tend to do things in a nice linear fashion. This is more than likely going to be a run on the market kind of situation. So we need to keep an eye on that. And then, the people who actually know about this think about power, they think about roads, they think about sewers, and they think about freshwater availability. Many coastal communities still pull groundwater out of the ground for their drinking water, and as the ocean rises, the fresh salt lens moves inland. And we've already seen many coastal communities having to go farther and farther inland for their fresh water. The estimate is that there's going to be about 150 million refugees by the end of this century, and certainly billions of refugees in the years after that. Right? And I don't think those are, I'm not saying those numbers to be shocking or to be provocative. I think these are pretty conservative kind of numbers. Now, what does 13 meters of sea level look like? This is Bangladesh with 13 meters of sea level. This is, one of those areas of the world that we care about from a refugee point of view. There are hundreds of millions of people who've got to go somewhere, and they don't really have anywhere to go. And this, we know this. This is the sort of situation that creates refugee camps, that creates instability, that creates social upheaval, social unrest. It's the reason why the Defense Department cares quite a bit about climate change and sea level rise. Is they recognize that these sorts of things are very destabilizing. This is Sacramento with 13 meters of sea level rise. So the good news is that California is going to get a whole lot more water to grow a whole lot more crops. The bad news is they're going to have to build a dam somewhere, in the San Francisco area to keep the seawater from going into this part of the world. Florida with 13 meters of sea level rise. I think I see a couple of markets that are fundamentally changed here. And then Maryland and Delaware with 13 meters of sea level rise. Delaware approaches, whether we ought to just say, okay, we give up, we'll go to 49 states, and we'll just let that one go by the wayside. A new Arctic is here. The disappearance of summertime Arctic sea ice is faster than anticipated and has had profound changes in tourism, has profound changes in shipping. So today, for example, we see lots of ships that sail across the Arctic every summer. Many of them go through the Russian waters. Russians charge. So whenever they can, they go through Arctic. Or they're waiting. The shipping community is sort of waiting and saying, okay, when can we go right across? Because when you go right across, you don't have to pay anybody. That's open ocean. That's blue water. And the shipping community is... Now, I put this other map up here, this one on the upper right, for a reason. This is you go on the internet, and you can still find many, many, many pictures of, what was back in the 1980s, in the 1990s. This is a map from the 1990s. And it basically shows the Arctic as a big frozen chunk. And I'll show you in a minute that that's not the reality anymore. Okay. So I'm going to show you a few animations. And a couple of reasons to show you these. One is I think these things have gotten a whole lot better. And if you go on the NASA website, you can pull these things down. This is the long-form version of this one. This shows monthly changes. And it's kind of interesting because you get an idea of how the Arctic works. It flushes ice out along the coast of Greenland every summer. And if it's cold enough there, more ice forms every summer. The white stuff here is the old ice. And you see on there the scale that's bouncing up and down is the amount of old ice. And old ice being 4, 5, 6 years old, being 4, 5, 6 meters thick, being ice that can withstand a summer's melting event. Yeah, Howard.
Yeah, Howard Bernstein, WSA in Washington. How do you know the difference, satellite sensor, between the old ice and the new ice?
Very good question. This is done by a couple of methods. One, there is a spectral method to look at this, but you can also track bits of the ice. And if they're still there year after year after year, you can actually add that up and figure out that, yes, that ice is old and it's thick. And then verification. You can go in there and actually measure how thick the ice is. What's important to recognize here is that as time has gone by, that white thick stuff has gone down and gone down and gone down. To the point now we're here in September 2016, you see we have a very different Arctic for two very important reasons. One is a lot more blue ocean water. Look off the coast of Alaska. All right. The second is that there's much less of this thick ice. And I'll show you in a minute just how important it is to keep the thick ice. By the way, if you don't like that long-form video, we also have a year-by-year video that has a much more dramatic look at the disappearance of the old ice. You'll see that it's episodic, as you might imagine. In 2007 and in 2012, we had meteorological conditions set up that blew a lot of ice out, didn't allow a lot of ice to form. Or the warmer waters didn't allow to. Keep in mind that the Arctic Ocean is warming up, and that whenever you've got that blue water out there, it's absorbing energy. Oh. All right, so you've seen how this works. Go faster. Come on. Yo, you. So just keep your eye on 2007. Yeah.
What's special about
You see that?
Howie Bluestein, University of
That
Oklahoma?
winds that blew all that ice out in 2007. Yeah, Howie.
What's special about the northeastern coast of Greenland that's where the sink for the ice is?
That's just physically where the ice is going out. It can't get down through the Barents, to the Barents Sea. So it goes out on the east coast of Greenland. It's a bigger opening? Yeah.
It's a bigger opening.
Bigger opening. Matter of fact, I have an ice core project going on today where we're trying to use an ice core to measure how much sea ice has been out there, so we can go back thousands of years and try to look at this. This is another way of looking at this. This is another NASA animation showing the multi-year ice decreasing as time goes by. What's important here is that the scale on here goes from about 5 million down to 1 million. It does go to 0, but the numbers get low. So you're looking at very small amounts of multi-year ice that are left. Yeah, John.
John Morales from NBC6 in Miami. So I'm having a hard time understanding why the rate of sea level rise at this point is 3 millimeters per year on average, whereas in the past, given similar changes in CO2 concentrations, it was closer to 10 millimeters per year. You're implying we're heading in that direction.
Yeah. No, I'm saying you're heading in that direction.
Excuse me?
I'm saying we're heading in that direction.
We're heading in that direction.
Beyond implication.
Beyond implication, yeah.
Right. But did I also understand that there are certain certain events within yearly, instead of multi-decadal type of timescales, there can be big increases in a short period of time. So it averages out to 10 millimeters per year over the long term, but you can have 1 year in which it could increase what? How much in 1 year if we had what would it take? In Antarctica breaking off or whatnot?
It would. So the good news is that you're not likely to see sea level increases on the yearly kind of timescale that are threatening or jaw-dropping. That's just not the way sea ice, or not the way land ice functions. So there's a couple of parts to an answer to your question. One part is, remember, it takes a long time for the ocean to accumulate the energy that 400 ppm CO2 would like it to have. All right, so 400 ppm CO2 is accumulating energy in the atmosphere. The ocean's warming up. The ocean's nowhere near the temperatures that it was 3 to 5 million years ago, or even 120,000 years ago. It's got a ways to go.
What's the lifetime?
It takes about 100 years to really warm the ocean up.
So when the last time we were at 400 parts per million, we were 10 meters higher.
Yeah.
Right? but there's a time lag involved in all
There's
this.
a time lag involved in all that. There's two time lags. One is you got to warm the ocean up. Then once the ocean is warmed up, it can erode ice. And then, to be honest, as a glaciologist, I can't tell you how rapidly that stuff is going to come out. Whether or not you'll see episodes of 5 meters in a century or whether it will average 3 meters in a century, I don't know. I mean, all we can do is look into the past and tell you this is what the system did in the past.
So last follow-up is the ocean temperature today, on average, compared to the last time we were at 400 parts per million, is nowhere near that point just yet. It's been warming, it's been absorbing heat, but it's not there yet.
It's not there yet. Give it another 30, 40, 50 million, 30, 40, 50 years. This is and I've spoken about this in the past, and this is one of the things I talk about quite a bit when I give public talks. It's an intergenerational issue. So we put the 400 ppm CO2 there. Even if it just stopped there, let's just say by whatever political or economic means, we stopped at 400 ppm CO2. Our kids and our grandkids are still going to have to deal with the energy that 400 ppm CO2 wants to put into the ocean. So sea level is going to rise no matter what. Right? The only way to stop that would be to take CO2 back out of the atmosphere. And even then, as we were talking about, have we triggered those ice masses, those unstable, that 14 meters, have we triggered that already, and can we stop that? And we don't even know whether or not we can stop that.
So in other words, we hit the solstice, but the hottest days of summer are still ahead.
Still ahead. Another way to think about it is, all right, you put that pot on the stove, you turn the heat on, it's just not gotten hot yet. All right? Give it time. It will get hot. Very quickly, the loss of old ice is important for a very important reason, and that is, so you see here in 85 and 2016, the amount of very old ice. That very old ice is important because annual ice is something that can come and go very easily. The Great Lakes is a good example of that. The Great Lakes used to freeze every winter, thaw out every winter, freeze every winter, thaw out every winter. I'm using Lake Erie here as an example. In 1973, on February 27th, Lake Erie was frozen over. It's all red. 2 weeks later, it's melted out. And that's the way this, that's that 32 degrees Fahrenheit, that 0 degrees C threshold. So as soon as you've got enough warm water eating away at it, warm air eating away at it, a little bit of wind action, you can make ice. It's that abrupt threshold nature of ice that's really important. My message to you is keep an eye on the Arctic because it is set up to change. And when it does change rapidly in the summertime, and you've got a lot more heating in the summertime than you had before, then you're going to see some very interesting weather. You're going to see some very interesting phenomena that we haven't seen before, to be quite honest. So keep an eye on that. This is one of my favorite slides. This is from a website called dogsports.com, which is the website of the Georgia football fanatic. And I pulled this directly. This is a screenshot from them. I don't think that you're going to find a whole lot of folks in Georgia who are strong, sea level rise type people. But it says here, and this is them, the USGS predicts that if ice caps were to melt completely, sea level would rise by about 80 meters. That's correct. Thank you very much. If we can get polar ice caps to melt only halfway, sea level will rise 40 meters, and the face of the Earth will change forever. Now is the time, Georgia fans. Trade in those efficient vehicles for a gas guzzler. Spray some aerosol. That happens to be wrong, but, they got an 80, right? Burn as much coal as possible. We can make Florida a thing of the past. The average Georgia football fan does not like Florida football, right? My point here is that, there are ways to reach pretty much everybody out there. Right? If you talk about them in terms of, all right, I want to make the Florida Gator football program a thing of the past, you've got an in. You've got a conversation started with somebody. You can talk to them about, yes, this is the way the planet functions. These are the way these things happen. Right? Yeah. I'm sorry. Well, FSU is in trouble too.
Tallahassee's still there.
Yeah. All right. Finally, I just want to. So I always end talks with these same slides, and I'll do this until I die. I want to talk a little bit about ethics. I want to talk about the reasons why we do these things. because we live on a water planet, we've talked about this extensively now, the impacts come after the causes by about 50 years or more, and that creates an intergenerational problem. Right? So we say we love our kids, but do we show it? And the answer is no, to some degree. Right? And that is because if we understood, I think, the physics of the climate system, if we understood the delays in that system, we would understand this better. But the fact is that we are indeed saddling our kids and our grandkids with huge expenses. And we got a great life out of it. Right? I have a fantastic life because of the energy that was available to us as a society. But I don't think it's fair to leave the problems, the waste, if you will, to my kids. Right? Thought number 2, population must be controlled. We don't talk about this, but this is something we need to talk about. Yeah.
The elephant in the room.
Population must be controlled. All right? I tried to get Jay Prater neutered, but it didn't work. Actually, it did, but we don't really want to talk about that. No. So the best and most lasting way to deal with population, I've talked about this before, is to empower women, economically and politically. And if you think about it, as a human society, we males, is there one? We males have dominated the system since time began. And the value of women in society still today in many third world countries is entirely around how many children she has. And there are parts of the United States where you can draw that correlation as well. Where women have political power, where they have economic power, 2 things happen. One is they tend to have fewer children per woman. And second, they tend to have those children later. Both of those things delay population growth and stabilize population. You don't need to do what China did, which is say you can't have any more kids. You can get to where you want to be by actually having more equity between men and women. And third, everyone has to care about a shared planet. As I pointed out, we got about 1.5 billion people without shelter. You got about 2 billion people who don't get enough calories or don't get the right calories. They're going to care about whether or not they can feed their kids. They are going to care about whether or not they can put shelter above their kids' heads. They're not going to care about what fuel they use. They're not going to care about whether they're cutting trees down. They're not going to care about the environment because they need to survive. So you cannot have a situation in which you've got 5 billion off here utilizing the planet the way we are, and the 2 billion over here struggling to survive, because those 2 billion are going to change the face of the planet regardless of what the 5 billion do. So at some point, you've got to think about equity. You've got to think about, we need to bring everybody up to at least some point where they can care about our shared environment. All right? And so with those 3 thoughts, I will stop and take questions. Thank you so much for listening.
Thank you, Jim. Let's get a microphone over to Jay. You got one. Go ahead, Jay.
Jay Prater, Cake TV, Wichita, Kansas. Very early in your presentation, you showed your population growth slide. Could you go back to that? This has been the elephant in the room for the long time, and sometimes we all know that smoking tobacco is not healthy for you, yet it's still a legal product. But just talking about the fact that it's unhealthy and encouraging not to use tobacco products has led to the decline in its use.
Yes.
When are we going to get there with this? My question to you is, where did this data come from as far as with the reduced growth rate, the world population will reach at the bottom?
That's observations. So the world population we hit 7 billion in 2013. Looking at the math of the curve, we're projecting 8 billion by roughly 2030 and 9 billion. Now, that depends on a whole bunch of things.
Well, my question is, why does it go from 15 years to 26 years? Are we counting on an increase in mortality?
No.
Is there going to be, why does that slow down instead of continue to decrease?
Thank you for asking that question, because around the world, we have seen decreases in birth rate that are directly related to an increase in the empowerment of women around the planet. So we've actually seen the impact of societies like China, India, etc., moving into more industrial, modern societies. And when they do that, women get the vote. Women get power. I mean, you can look at it. You can look it up online. Women don't even, I mean, there's still many, many countries around the world where women can't vote. Right? But that number's shrinking, and it's shrinking relatively rapidly. So the impacts of the impact that has on population growth is measurable, and we're seeing that today.
And so
Now-
you're able to quantify it to come up with this number?
Yeah, you can, yeah.
And in addition to the empowering women, how is that also potentially offset by faiths that encourage reproduction?
Yes. I can give you an entire lecture on population if you want.
I'm sure you can.
As a matter of fact, if you look at the number of... If you look at the number of births per woman across the United States, there are pockets, some of which are quite... So in Utah, it's a higher number. And it's a higher number because of faith-based issues.
Thank you, Dr. White.
Thank you. Yeah. Yeah.
Greg Fischel, WRAL Raleigh. As I've been listening to you for this whole time, I haven't sensed any, the word I'm looking for, exaggerations. I haven't sensed any advocacies or anything like that. I guess the only thing that I'm concerned about is that I think there's two forces, they're not science forces, but that are pretty scary in this day and age, and one is politics and one is religion. And I'm a person of faith. I don't think that science and religion are mutually exclusive. But we live in this age right now where confirmation bias is encouraged.
Yeah.
And I guess I'm curious as to, how optimistic are you that we're going to be able to eventually knock that out?
I'm inherently optimistic, but I'm a realist. And I share with you a couple of things. I'm also a person of faith. I also see that a lot of the forces that we need to harness for the future are not being harnessed. As a matter of fact, they're being fought against. And politics being a big issue there. I don't know. Like I said, I'm inherently an optimist.
Sure.
I believe that we're smart enough to use the brains that we have. I believe that conferences like this are a way in which we get the information out. I think that in the end, education and information trump ignorance and are able to move the needle. Now, whether or not it can move it fast enough, whether or not, whether or not Miami's still a market in 50 years or 100 years, that's a hard call. I hope the needle gets moved.
Right.
But it's not, as a scientist, this is not in my hands, really. My job is to say this is how it works. Policymakers, you've got to take this stuff, you've got to figure out how to digest it, you've got to put it into the systems and move it along.
Gotcha. Thank you.
Well, Todd Santos, CBS Buffalo. Greg actually just in a very eloquent way asked part of the question I was going to ask. The other one is we talked so much about forecast certainty when it comes to weather forecasting. As far as sea level rise, I know there are a lot of nuances in the rates of change and this. And when you showed, Norfolk and San Francisco Bay and those areas, how confident, what's the confidence level in that type of rate of change over the next 30, 50, 100 years?
I think the conservative number among the ice scientists for 2100 is about a meter of rise, and it's going to continue to go up as the ocean accumulates heat and as the ice begins to respond. It'll go up, and it's going to take that classic S-shaped curve where you get a really good bang for your buck, and then it kind of flattens out. Exactly how that plays out, really, glaciology started as a science with the International Geophysical Year in the late 1950s. So we don't have a lot of observations. We don't have a lot of really good hard physics about how these large ice sheets function. What we can do is look in the past and say, yeah, 3 times faster, 3 meters a century, certainly possible. As a matter of fact, that's the average. That's what we'd expect. I think the bigger questions here, Todd, in the end, the bigger questions are going to be whether or not there's reversibility in the system. Because I think we all know how human beings function. We'll start to, Miami Beach will start to get less and less habitable. People will scream more and more. Norfolk will scream more and more. There'll be this point where you go, oh, this is not good. We don't want to see this happen anymore. Let's do something. And there are things that we can do from a geoengineering point of view in terms of pulling CO2 out of the atmosphere. We can actually get quite, but whether or not we can stop that ice is a real fundamental question. And that's one that we've got to answer at some point in the future. Because if you can't stop it, if it's one of these big freight trains that once it gets going, you can't stop it, that changes, to me, the whole dynamic of the policy discussion. Is that a good answer? Is that a decent answer? Dave, they give up and I give up.
I have a question.
Okay.
From a person online that's been watching by the name of Joe Whitty.
Ah! Hi, Joe.
Joe says, Jim White, if you had a large NSF grant tomorrow, what ice research is next on your list to fill in any knowledge gaps?
Thank you, Joe, for that question. I've written several proposals, and they've not been funded, Joe, to NSF. We're trying to look at a place called Northeast Greenland. The Northeast Greenland. So in the northeast part of Greenland is one of these marine-based ice systems. It's like a meter or something of sea level rise, 1.5 meters. So it's not big, but it's important for understanding the dynamics, getting back to your question. How fast can these things occur? It's the first ice core we'd actually drill in what's called an ice stream. Ice streams are places where ice is moving at a pace of about 50, 60 meters a year, which is pretty remarkable. When you stand up there on the ice sheet, it's hard to believe that this is moving at 60 meters a year, but you put some bamboo poles out there, and sure enough, within a couple of weeks, you can see that motion has occurred. We've tried really hard to get a project funded to go and work with the Danes and with the Swiss and with the French to try to understand that system. We've not been able to get that funded from the American side. That's where we're going right now. Thanks, Joe.
Jim, thank you very much.
Thank you.
Terrific.